you are losing a lot of value if you can't make it. There's an enormous return on investment for any company that's paying a developer a reasonable developer wage and sends their developers here. I can't tell you how big of a mistake it is not to send someone to CppCon.
All right, I think we are ready. And I'm live, obviously. So let's get going. Hello, friends and enemies. First of all, let's get rid of that title slide and use the real title slide. All right. This talk is fairly long. You can see I've got quite a lot of slides. Do please ask questions as we go. How long the talk is depends on how much interaction I have. So I'm just going to go through it, and there may not be time for questions at the end. So if you have questions on a particular slide, shout out. I'll just do my best to control the time. Okay.
Please use the microphone for questions for the recording.
Yes, you can use the mic for questions. You can come up at any time. If you forget, I will repeat the question to keep the recording happy. Okay. All the code on these slides you're going to see is real. It is Boost licensed, so you are free to use it. However, I may have made mistakes in translating it for slides. The usual disclaimers apply. Assume also that I've removed cruft, so assume it has no discard and no except where you'd put it and context expert and things like that. But if you do spot errors, please point them out. For those of you who don't know me, I used to work in games. I started programming C++ in the mid-90s, had quite a long career in games. For a while, I worked in finance. Now I work at Intel with Michael Case and Luke Valenti and an awesome team. And this presentation is the story of me learning things from reviewing the code of my team and figuring out how to make their jobs easier. Sometimes I achieve good code, and I always strive for it. So, all code is bad. Does anyone believe different? But as humans, we're really good at copying patterns, right? And when we're working in a domain, when we're domain experts, we don't realize that this code is bad because it kind of works, it does the job, we're used to it. We don't see the pain points in our own domains, right? And it's really difficult for us to step back from that and take a higher level view, because when we come to solve a problem, we always think about, I know, okay, here's a problem in my domain. I know the domain really well. I can figure out how to solve the problem. I'm a good engineer. I can figure it out, and I know how to implement it, and I go away, type, type, type. But a lot of what I do, and a lot of what I have done over the last 2-3 years, and it helps coming new onto a team, sometimes coming new into a domain. I'm seeing what people are trying to do. I'm spotting patterns. I'm spotting use cases. I'm figuring out ways that we can raise the level of abstraction, right? People have an intent. That intent is correct. Sometimes they don't realize that there are easier ways to do things, or the easier ways might not exist yet, and it's my job to make them. And like I said, in some ways, it actually helps that I'm kind of new to the embedded space, because I don't carry with me a bunch of past knowledge about how to do this thing. So the environment I work in right now, it's embedded, it's bare metal, there's no OS, it's super low level, but it is still C++20, it is still contemporary C++. Now, most of my team, to their great credit, 5 years ago, most of them were writing C. And they were thrown into, by Luke, and by Michael, and then by me, they were thrown into this contemporary C++ code base, which is full of contemporary C++ idioms, some template metaprogramming, lots of under-the-hood tricks, and they came up to speed really quickly. And that's to their great credit. Now, I work on firmware. A lot of times, the hardware spec bleeds into the firmware, and we get this kind of over-specification problem where we actually want to step back. Because firmware is software, even though we don't use that term much. And we want to figure out what the real problem is we're solving and abstract it a bit oftentimes, right? Now, you might think you know what it means to write C++ on embedded systems. The truth is, most of the advice and the code you find out in the wild has not kept up with the pace of C++. In particular, C++ 20 and beyond. Now, I'm not even talking about things like prohibitions on exceptions or runtime allocations. These are still legitimate choices, but the gap here is like, while you don't want to use string at runtime, it's totally fine to use it at compile time, right? Things like libformat have an interface which involves strings and the std except header, and it does compile time formatting, right? Never hits the runtime, perfectly fine for use on embedded, for example. But if you don't have that header in your toolchain because your embedded toolchain provider doesn't provide std except, because why would you use it? Well, obviously, you don't compile. But you can use it. So we pretty much use all of the STL at compile time. That's the sort of mindset here. So we want to get away from magic numbers, magic operations, having to think about state. We want this kind of best sense of abstraction. Now, we tend to be quite happy in programming with the idea that magic numbers are bad. We'll introduce a named constant or whatever. We'll go about our business. We're less observant. We tend to be less observant to the idea of magic operations. So we're still quite happy to say shift here, add here, mask there. We think nothing of it because that's what the spec says to do. Like I said, the hardware spec bleeds into the actual code. But there's often a better way to express ourselves. And this talk is a collection of those better ways. So let's start with the small stuff, quite literally, because oftentimes we're dealing with bits. Not bytes, but embedded code is full of bit masks, bit calculations. By the way, how many people in the room are in some kind of embedded dev role? Yeah, maybe more than a third, probably slightly less than half. By some estimates, it accounts for about a third of C++ engineers in the world. So here's a really common thing. Like I say, we're starting off small. You have n bytes, and the uint32t is the vocabulary type that the hardware uses overwhelmingly in our case. So it is the sort of lingua franca data type that we use everywhere. So you have bytes, and you want to compute how many 32-bit words you use. So who's written code like this? Yeah, many. Who? Recently, even? I mean, yeah, people do it. People do the first type. If you're lucky, people do the second type quite a lot. It's an easy thing, right? It's very easy. It's close at hand. It just does something that you need right now to calculate something that you need right now. And does it matter if it's using some magic numbers? Well, this is perfectly readable, right? Well, maybe it is readable. But instead, I would like to have a more general solution. So here, and you're free to criticize any of my current solutions, by the way. They're always a work in progress. But here's what I have right now. Is it more readable? Well, it might be more readable, but less legible in a sense. But it says we've got t's, and we've got n of them, and we want to know the size in u's. And this is correct now in every case, and it's dependable. Now, if you know this at compile time, so also you can do convenience aliases like sized 8 for sized uint8t, for example. If you know it at compile time, you can also use a UDL, for example, and you can be very terse indeed. You can say something like this: I have 48 size 8 things, and I want to convert to size 32 things. And I use Z for a size UDL, just because that seems reasonable and it's available. So, you might think this is, at first glance, not something we're used to, but I think it is quite readable. It's terse. It's a simple operation. We want simple operations to be terse. If anyone disagrees, you can argue with me at any time. Now, as well as that, we do a lot of bitwise operations. So it's 2025. I still see most example code, to be honest, for interacting with hardware that does manual bit shifting manual masking. Who has that kind of thing in their code base? Yeah, a lot of us. I mean, I do too. To be clear, I'm trying to make it better, but there's a lot of this. And we think it's easy to read because we're used to it. But I would say it's not typically easier to read than if we have a good abstraction. And it's also not typically very safe unless we put static casts in. We'll see that in a minute. So this is typically how we might make a bit mask, right? We've got some field which is from bits 7 to 3 inclusive. So we're just making the mask of the most significant bit. We're making the mask of the least significant bit. We're taking the one away from the other. That gives us the mask between those bits, right? Now that's okay-ish if you can ignore integer promotions. But it gets much more hairy because what is the type of x here? We're taking away 2 chars. Was that you, Barry? That's right. It is int. Obviously, yes, obviously it's int, right? Now, anytime you want a promotion, and it's signed int at that, right? And we're mostly using with unsigned type. Even if these were unsigned uint80s, it's still int. And of course, people want to be safe, so they do strange things. Here's another thing we see, right? Because we are wanting to compute something involving that very top bit, we might see code like this. Everyone knows what's wrong with this? The clue is in the title of the slide. Yeah, it's undefined behavior because we're shifting the type by its width, right? In this case, 32. So, you know, these problems are very obvious when I put them up on slides, right? But when they're buried inside a multiple 100,000 line code base, they are much less obvious. So how about if we want a bit mask, we just ask for one, right? And we can do that with compile time values and template parameters, or we can do it with runtime values in regular parameters. And we'll ask for the type of the thing we want back, the uint80. Now, I think this is nicer, this is more readable code. This is safe in all cases. I mean, actually, the safety depends on whether or not there's a runtime check underneath sometimes. But also, you know, we have tests and we run tests with ubsan, so that helps too. Now, as well as making masks, a lot of the time we do bit packing and unpacking, right? And we do things like this. And if I were to ask everyone to raise their hand again, I'm sure half the room would raise their hand that they have code similar to this. So I see a lot of code like this. Of course, actually, I don't see code like this. What I see is code like this, right? Does this look familiar to anyone? Of course, dear audience member, you know that not all of these casts may be necessary in this case, because you are here at CppCon. You are a sophisticated, savvy, modern example of a C++ expert. But in the real world, authors and reviewers of code, they just want this to work. They don't want to be concerned every time we're thinking about which integer promotions happen and knowing that minutiae. And somebody like me comes along and turns up the warnings and turns on the linter, and they want it to shut up so that they know their code is okay. So they just put the casts in. Now, I don't blame them, but I do want to keep those linters and warnings on, and I want to make their life easier. So when they're doing bit packing like this, I want them to just do bit packing like this, right? If they're doing bit packing, you might as well say, let's do some bit packing. Again, ask for the type we want, put the high and low bytes in there, or the high and low words in this case, right? Because this, and we can bit unpack as well, right? Same kind of way. And again, we'll ask for the type we want those 2 high and low values to be. And we can write nice overload sets of these that take, you know, for example, you can pack 4 bytes into a 32-bit word, or 8 bytes even into a 64-bit word, and you can make the overload sets, and then you have this abstraction, and it just works. Of course, just like this, it works for all sizes that you are likely to want. And it's just a nicer way to say it. Like, I don't know any other way to make it clear, really. Now, this is for packing and unpacking on, of course, the 8-bit boundaries. But sometimes we have non-8-bit boundaries to work with, right? Sometimes you might have a register that's got some fields in it, and you might just want to say destructure the thing into the fields. Well, we can do that too. We just call it bit destructure. It works exactly the same way as bit unpacking, and you say where the boundaries are. And of course, you say 2 boundaries if you want 3 items, right? And then you get the right things out. Now, I've put them on the 8-bit boundaries here, so it's easy for you to see what's going on and not have to figure out bits in your head. But they work anywhere. Taking this even further, we end up, of course, with whole definitions of fields and whole definitions of messages, which can be overlaid on arrays, and they can read out their fields as you want. And it looks something like this. But this is really going down the rabbit hole, which is another talk. Yes?
What about endianness on the previous slide?
Well, yes, what about endianness? You've noticed it. So when we bit packed these things, this is big endian, right? Because we're saying 1, 2, 3, 4, 5, 6, 7, 8. In some sense, it's high to low. In this slide, it's low to high. That is completely correct. Now, that is a current design choice. That might change, right? It is that way to be least surprising in a sense. And you definitely want the unpack to be in the same order as the pack. And you want the pack to be in the same order as you would write the number in text, in code. So that's why that decision is that way this time. Thank you for the question. The question for the recording was, what about endianness? But in this case, because it's natural to count up from 0 in the bits of the template arguments there, in this case it is little endian, you might say. But these are things that are designed somewhat for least surprise. They're always open to change if I see in code review people having problems with them, right? But for the moment, that's how they are. But thank you for the question. Okay, so, we've seen simple things. The point for this talk is that there's a lot of utility in these simple constructs that just replace somewhat established patterns that people think are easily readable, but in reality, those patterns are just easy because they are historically what we've done. Here is another common pattern. So how many people do this? So you want enum bit flags. It's a thing, right? So, well, how many people do this? So you define an enum or an enum struct with power of 2 values. Are you still with me? You overload some bitwise operators. Are you still with me? Yeah. Maybe you jump through a bunch of hoops. Maybe you use macros. You convince yourself you have more time. You definitely form an opinion about ADL here, right? I think maybe we've been doing this wrong, and there are multiple talks and libraries that help us do it wrong, and blog posts even. So, is everyone okay with this expression? It's fine, right? It's fine. Looks fine. Okay? I'm starting easy, right? So if I'm assuming you're okay with this. You're okay with this as well? Yeah? Sure? You okay with this? Is Dan in the room? If you're a chemist, you should be fine with this. All I've done is relabel things. Sulfur is 16, nitrogen is 7, vanadium is 23. You okay with this? Same thing. All I've done is relabel. If you're a Pokemon trainer, this makes complete sense, right? But somehow we're okay with this, right? I didn't even, there is a Pokemon at number 23. There is an element at number 23. There is no element of E at number A or B. Right? X is not even a nameable member of the enumeration. The space is not dense. Is this type safety? I don't know. I think we've been confusing labels with numbers. Now, under the hood, the register value is a uint32t. What we actually want is to name the bits, right? But that's separate from pretending the names are the values. So, why haven't we been using bitset? I think std bitset just doesn't offer the interface for this, and that's the only reason. But if we want to treat a register like a bitset, Let's do it. I see Dustin nodding. Have you done this as well? Yeah. It's kind of like, I don't know why people aren't doing this. And indeed, some people are, and they probably have the same thoughts. So let's just use the interface that we want. We want to name the bits. So let's just name the bits in the enumeration. Let's make a bit set over that enumeration type. This is not a standard bit set. So we'll tell it to set the bits A and B. And then we can index it with B, or we can ask it to set C. We can use the bit set operations that we're used to. And then when we come to pull the number out of it, we can just say, give me a number. Let's have a to operation that's templated on the type, right? I think this is better type safety. We didn't need to shift those bits in the enum. We didn't need to pre-compute anything. We just needed, by convention, a max in this case. And it's really not very hard to make a bit set that does this. It's just that std bit set doesn't do it out of the box. The interface of std bit set and many things in standard are a bit weird because they represent use cases that people who proposed it had. But I think this is just a lot less hassle. Okay, let's go from bits to bytes. We've dealt with bits. Quite often we need to deal with bytes. So let's examine a use case. Here's a very common use case. We have some table of data that's provided at some well-known address. It's to be interpreted, right? It's a table of data. It's an array. But sometimes I'll need to look at a byte there. Sometimes I'll need to look at a 16-bit word. Depending on what that is, then I might need to look at a 32-bit word, etc. And of course, the code looks like this, doesn't it? Because of course it does. We've all seen code, I think, that looks like this. It happens all the time. So we've got a table at some well-known address, and we're just interpreting it. So we're looking at a byte. Based on that value, we might need to read a different size thing. And this is, of course, using reinterpret cast. And when we use reinterpret cast, what happens? Undefined behavior. It wasn't JSON, but it is practically certain that you have UB anytime you have reinterpret cast in your code. If you doubt that, go talk to Jason Turner. It is so difficult. Even when we think things like, oh, it's okay to read from a byte pointer or a char pointer. No, it's not, actually. We keep on discovering new ways that the standard is deficient here, and it's not. It is basically impossible currently in C++ to access the underlying object representation of an object. And the reason for this is that we don't just run C++ on hardware, we run it at compile time in the constexpr virtual machine, and the interaction of that is what's caused us to look carefully at these things. Basically, there's no getting around using memcopy or bitcast. And our mental model of those objects backed by an underlying store is just wrong when it comes to how the compiler treats constexpr stuff. So, anyway, people want to do this, so I'm like, well, let's try and make a safe way. So I call it byterator, of course, because it's an iterator over bytes in some sense, but it allows you to peek, read, or write any integral type by using read U8 and things like, peek U16 and things like that. And now we have a safe way to do what we actually want to do. Like I said at the top of the talk, like the domain expert's intent is correct, right? I'm not stopping them from doing what they're trying to do. I'm just trying to make it easier and safer. So byterator can do these things, and under the hood, there are a very few functions which do this, and those functions are tested with ubsan, and they use memcopy, and hopefully they do the right thing. There's always the chance that I could have made a mistake, but it's a lesser chance than having reinterpret cast. So this is about the best we can do, I think, at the moment. It has some nice features, like we can control the return type, right? So we can say, read a uint8t, but return it to me as a uint16t. This is really useful, especially when you want a return value as an enumeration type. Okay, let's talk briefly about std optional. We want optionals in our interfaces. We want deferred construction, which is a great use case for optional. These are useful ideas. What's wrong with std optional? Well, many things, some of which Steve has fixed. But in the embedded sense, a stood optional uses more space than it needs. Sometimes this is a problem, right? You put an extra bool in there, and alignment and padding means that you typically have a doubly sized integral type. A lot of the time, we have a sentinel value that we can put in there, or a tombstone value, as it's sometimes known. So I have an optional that allows that, and people can use it, and it's just the same interface as optional. They can do it by putting in a tombstone value at the time they want to actually declare it, or they can override a tombstone trait for a particular type, and then it will use that. So characteristics of this optional that make it suitable for embedded work, there's no exception use here. If you access a disengaged optional, you don't get an exception, you get the tombstone value. And I provide default tombstone values for null for pointer types and for floating point types. Now the obvious tombstone for floating point types is nan. Why did I not use nan here?
Does that be a valid value?
No, nan is not considered a value. Sebastian?
You can't compare the value to the...
Yes, you cannot compare nan to a tombstone value. So that's why I used infinity. Some extras. Multi-argument transform. I have a whole talk about that, but it's really useful. The standard keeps on putting things in member functions, which kind of binds it to being single argument. But if you want to do kind of functional style programming, you want multi-argument transforms. So we put this in, and then we recognize another use case from code reviews. A lot of times, we're just using optional for deferred construction. And so since we're doing that, we want a specialized sort of way to point out in the code, and we call that cached. And it's an optional under the hood. It has really the same kind of interface as optional with a couple of extra things. And it just takes a lambda that when you access it, it will call that and do the deferred construction. Yeah?
Because you call it cache, does it imply invalidation, or is it more like a lazy option?
Does it imply invalidation?
Yeah.
It implies that, yes, you can choose to invalidate it in two ways. So yes, it's a lazy optional. Optional is a lot of times used for deferred construction, right? And that's what cached does. That's the idea of cached. But there are two ways to invalidate it. You can reset it, and that will mean it lazily, next time you access it, it lazily computes. Or you can refresh it, which means it recomputes right now. Now, again, after we introduced this, then we discovered another use case. Well, a lot of times we have a cache thing, and it's only ever cached once at load time, effectively. So we just made a small variation on that, and we call it latched, right? So this is cached without the reset or refresh functions. Now, this being C++, you can always pull tricks like, destroy and reconstruct in place to get around this. But if you did that, it would stand out in code review, right? And you can always start with latched and then move it to cached if you discover that you need to reset it, like they're basically drop-in compatible. It's a pure extension on the interface. All right, let's talk about time. Time is tricksy, especially in the embedded space. So here is a scenario. For example, your microcontroller has a 32-bit register, and it just continually counts up microseconds. This is a fairly common thing. Anyone program a microcontroller like this? Several people. What's the problem here? Well, the problem is that 32 bits worth of microseconds is not very long, really. And because you really need to treat time as signed, you're going to have half of that bit space in the past so that you can know when things have expired, right? And you've got half in the future, which means you've only got 36 odd minutes total in your time universe. And you still need to know when a timer has expired. Now, the problem with 36 minutes is it's way too long as a human to wait for something to occur. If you get an error and you then have to wait 36 minutes, no good. On the other hand, it's way too short for a time scale of human things. Like you could go away from your computer quite happily for half an hour, get a coffee, come back, and something is screwed up. We see things like, so what are we going to do here? Fundamentally, we see these things like half-range checks, right? So again, this is not perhaps the way that we, as a savvy crowd of C++ experts, would write a half-range check, but it happens. And this code is kind of fine, right? But then someone comes along and they helpfully refactor it, and they say, oh, I can, inline that into there. Does anyone see the issue here? So if T is uint 32T, we're still okay. Yeah, but if T is uint 8T or uint 16T, now, when you say not X, that's promoting to an int. And half of the max, the max is going to be -1, right? All the bits, because you're just bitwise knotting it. And now -1 divided by 2, well, that's 0. So integer promotion is not your friend. Now, I know you want to say use numeric limits or whatever, write it differently, and I absolutely agree. But the fact is, things like this exist. It's real code, it happens. And we don't want to see these kind of things causing bugs for whatever reason. So we just want this kind of thing abstracted into a type. And that type is a rollover T. Now, the idea is that you've got this 30-second, 32-bit microsecond timer, and it's rolling over, right? So you want a type to represent that. You want a type where half of the bits are going to be in the past and half are going to be in the future. So a rollover T of your unsigned type supports this, and it supports all the normal arithmetic operations, mod 2 to the n. Now, if you have half of your bit space in the past, which way is the past from your point of view? I think it's over there. So you're in the past, now is here, some bits are in the future, and that window is always rolling, right? And you want to compare, right? Now that behavior is easy to implement. I mean, it's not easy, but it can be done. I chose to delete the comparison operators on rollover T. Does anyone know why that is? Like operator less than is deleted. Because
If it's continuously rolling, you might have a situation in which a time value in the future is actually like integrally less than a time in the past.
yes, if it might be integral, yes, but the less than operator takes account of the half range.
Sure, it's thinking more of like the register value.
The register. Okay, keep that in mind, yeah? Atomics, no, atomics aren't the reason. Here is the reason, and we'll go through it on a 3-bit counter to make it really easy. So imagine this scenario. You've got 0 less than 1, 1 less than 2, etc. 7 less than 0. The less than operator is non-transitive. Now, that's a thing, but it's not a good thing to pass a non-transitive comparison operator to sort, right? So we have a comparison operator, and it's called, I call it complex. It's a member of the class. It's like rock, paper, scissors, right? Operator less than would not fulfill the requirements required by algorithms like sort. It would be dangerous to leave operator less than lying around. So I don't leave that lying around. Now, in general, I don't want to outlaw danger, which is why I still have complex if you want to use it, right? As a library writer, it's not my job to tell you you can't do that. Because you're the domain expert. You know what you want to do, your intent is correct, you know what you need to do, and sometimes we need to do dangerous things, right? I don't want to prevent you from doing dangerous things, because that would prevent you from doing clever things. But I do want to provide you with a safe interface for everyday use, and I do want to make sure you know when you're doing something dangerous, which is why I do that. I want you and your code reviewers to be deliberate and informed when you are doing dangerous things. Sometimes we need to, but we shouldn't be doing it without knowing that it's dangerous. And so if you know your data is suitable for sorting, like you know that that rollover case won't happen, that non-transitivity won't happen because all of your data is collected into sort of 1/2 of the bit space, you can totally still sort it. But by the same token, I don't want dangerous interfaces for everyday use, right? And there's another problem with naive time interfaces. So here's a very simple part of an interface that might be in a hardware abstraction layer that just allows us to say, what time is it now? And schedule something to run in the future. What could be more natural than this? We have loads of things we want to do with this, right? We want to wait some time before doing something. And this interface looks clean, contemporary, nice, but there's a problem. Does anyone see the problem? Problem only maybe if you're working in like embedded space where you have interrupts. At the point where you compute the timeout, you're fine. But then other things happen in the world. Then you might even go to sleep. The programmer closed the lid of their laptop and went to get coffee. They come back 40 minutes later, past that rollover time, and now the thing that was slightly in the future is a long way in the past, but now it's a long way in the future, right? It's kind of rolled over. It would have been a long way in the past if they'd come back before that 36 minutes, but because they just overran it, it's now a long way in the future, and now they're waiting forever for something to happen that should happen in the next 5 milliseconds, right? Any interface that allows us to compute a time point separately from scheduling it is going to have this problem, and it's incredibly difficult to find these problems in the small scale. They only show up in the final system, and they do show up, don't they, Michael, in the final system? Because we humans are very bad at reasoning over time. So instead of dealing with time points, let's just deal exclusively with durations. This is what we wanted to express anyway. We wanted to say, run the thing in 5 milliseconds. So why were we computing the timeout and then saying run then, rather than just saying run after that? Let's not be wrangling timeouts manually. Or better, we could even use a senders-based interface. And we can say, give me a timer scheduler for 5 milliseconds in the future, and schedule it, and then do my thing. Or in the second case, we can say, give me a timer scheduler, I want to do something periodically, right? So now control over those timeout computations happens under the hood, where danger can be limited, where we can have one implementation that we test to hell and back, and we reason about properly in one place, instead of these things being spread all over the code and having to reason about every code review. We want one place to reason about these kind of things where interrupts can be tricky. All right. Any questions before I move on? Any observations? Anyone who thinks this is a terrible idea? No one willing to speak up? Okay. Let's talk about thread safety. Or in fact, interrupt safety, which is really kind of the same thing in different guise in the embedded domain. Now, the embedded domain often presents us with primitive constructs which we need to build abstractions out of, right? We don't have even the fairly low-level constructs in the standard library, things like mutex, barrier, semaphore. Those are still fairly low level, like they're not sort of allowing us to reason at task-based level. But we don't even have those in embedded. So we do what we can. We basically have one tool many times. We can turn interrupts off and on again. Luckily, this happens to be very cheap. So basically, we have this global critical section. So let's see what we can do with that abstraction. Well, we can provide a function saying, just run this function that I'm going to give you under a critical section. That's a very, very thin layer of abstraction on what we just saw. Nevertheless, we'll build on it. In fact, it's slightly more than that oftentimes. Oftentimes, we want to run a function when a predicate is or becomes true. So we'll allow the user to pass some predicates in, and then we have code that looks like this. We naturally can write an RAII type that disables interrupts. Who was in Ben Sachs's talk yesterday? Ben gave a really good talk about implementing Atomic that touched on some of these same ideas. Okay, so this is fine. Now, the issue with the abstraction here is that it works fine on our platform, but we also want to test it, right? If this is really raising the level of abstraction, we should be able to run this on desktop tests. Now, almost all of the work that we do, that Michael and I do, involves handling concurrency. Like on one of the slides at the beginning, there's almost no number crunching because these microprocessors don't have much capability. But what they do is marshal I/O like crazy. And they do it, so 95% of the code is doing I/O, and it's doing it concurrently, and it's wrangling interrupts from different places. And the problem is, how do we test this on the desktop? How do we turn this into a desktop test? Well, we have this global mutex or critical section idea. We don't have parallelism, we don't have hardware level parallelism, but we have concurrency. We don't have any of these other standard things. And so here are some of the problems that we see if we just have this abstraction. We have two unrelated pieces of code, two unrelated pieces of data, right? But because the lock is sort of global on desktop, we wouldn't necessarily recommend that because it's contending. But this passes by unnoticed on the platform hardware because it's all there is, right? But this isn't really the best way to write desktop code. We might have brittle correctness, right? We might, on the platform, accidentally use shared data in two different places, and it happens to work today because these two different places happen to be called from different priority interrupts, and they don't actually stomp over each other. So we've got accidental successes happening. We don't want that either, because you never know when that's going to break, fall apart. Again, usually in the whole system, not in a unit test, where it would be actually evident. We have other kinds of brittle correctness. On platform, that interrupt off and on RAI is actually like a recursive mutex on desktop. And that, I don't know about you, but whenever I think I need to use a recursive mutex, I just feel bad. I just feel like I haven't structured my code properly. And yeah, you don't want to be doing that a lot, I feel. Anyway, so on desktop, we could implement this critical section with single global recursive mutex, and that would work. But for those reasons, I don't think it would be much good. In particular, the reason of like accidental success. Like, I don't want to write things that are brittle, because even in the world of micros, things are getting more powerful all the time. There'll come a day when we have actual hardware concurrency. There'll come a day when the constraints I thought about today no longer apply. But I want the same interface in both places. So here's what I do. I inject the concurrency. I use this global API injection pattern. So this is what the calling critical section function looks like. We pass it a function that we're going to call, and it delegates to this policy. Now, how does it find the policy? It finds the policy through a template, through a variable template, which it gives some dummy args right there. Those dummy args, for any given call site, that's always going to be an empty pack, but it still uses it to find the right place. Now, and it has this unique template parameter. This is doing the job of a mutex, if you like. This is like naming a mutex. So by default, it's different at every call site because it's a defaulted template parameter. Of course, parameters come from call sites. Template parameters are no different. Every call site will get a different lambda here, so every call site will get a different type. But if we want to use the same type, for example, in a queue structure, we can just make a tag type, call it mutex, call it mymutex, whatever, and then we use it. And now, on desktop, this is accessing the same mutex, right? So this is actually one mutex protecting what we want to protect. This is correct on desktop. And on platform, of course, it's our implementation. It's fine. Now, this is still only per type and not per instance. We're not quite to the level of granularity that we would totally want, but it's a way better than what we had. Now, the desktop test policy, like I said, it just uses a mutex, and that type selects which mutex it uses, and it does what you'd expect, a lock guard, and then return the function. I omitted the predicates here, but and on platform, well, we just use our interrupt disabling RAI type. We saw that before. That's all that's available. Well, now this works pretty well. So desktop tests now can have the same calling code. They can have the same thing. The only thing that changed is that very low-level implementation. And we don't have any more working by accident code. We don't have any more recursive locking reliance. We can run thread sanitizer on the test. That is huge, right? If you can run thread sanitizer, if you have threaded code, you ought to be running thread sanitizer because it will find bugs that you would have no hope of finding otherwise. What we've done is we've turned interrupt race conditions into data races in desktop tests that can be caught by tooling. Huge. Now, I mentioned Ben's talk about atomics yesterday. Turning off interrupts is not quite the only way to ensure thread-safe data, because we do, on various embedded platforms, often have some form of atomics. But there's a problem. And let me illustrate the problem. What do you understand by this code? By which I mean, what would you expect on writing this code? There's no tricks here, just a plain old atomic int, and we're incrementing it.
X is supposed to be 43.
X is supposed to be 43, sure. I think beyond that, what would be your expectation of the generated code?
Expectation or reality?
You would expect probably that it uses atomic instructions. Am I right? Whatever that means for the platform. Doesn't this tell us that we are programming to an implementation, not an interface when we use atomics? This is the problem. You'd expect an atomic instruction. The problem is that your embedded device probably doesn't have very many atomic instructions. It might have one or two. It might have an atomic exchange of a 32-bit value, and that's all, for example. So std atomic suffers from this confusion of interface and implementation. We use std atomic expecting an implementation, strangely. But that implementation just might not be able to exist. You might not have vetchad or any of those other things. You should watch Ben's talk from yesterday because it touches on some of the same points. Of course, the other problem with atomic is that it lies at the heart of the C++ memory model. It defines how actions become visible. And that also is part of the interface, and shouldn't be locked to one particular implementation. So we expect these two things from atomics. We expect non-preemptiveness. The operation should be atomic, right? Unable to be divided, literally, from the etymology. But also we expect visibility from the C++ memory model. So std atomic is this sort of confusion of ideas. We're programming to an interface, not to an implementation, not an interface. And of course, on platform, you might just have, this might work, right? Except that if you forget to align the variable, you get a processor exception. I've seen this happen because your exchange instruction requires alignment. Now, you might say this is a problem with the toolchain, and I agree, it is a problem with the toolchain. Nevertheless, it exists. It could be also that exchange has more constraints than you first realized. Now you align it properly, but because it's a bool, and the next 3 bytes in memory are something else, well, the processor is going to generate an exchange instruction on the properly aligned 32-bit value. Now when you do that exchange, it's going to clobber the next 3 bits in memory. I've also seen this happen. And of course, the problem of you just don't have that very many actual atomic instructions. There's no single instruction that does fetch add in this case. Std atomic is, in most toolchain implementations, it's really trying to use atomic instructions. And if it can't do it, sometimes it ends up calling intrinsic functions in the toolchain that implement these operations comparatively really expensively. What you actually wanted was atomic access, visibility guarantees from the memory model, as cheaply as possible. And in fact, it would have been way cheaper to do that simply by turning interrupts off and on in many cases. So yeah, atomic has a meaning for the interface, not the implementation in this sense. I don't actually care if it uses atomic instructions. I care about if it does things correctly and efficiently. So again, my implementation of atomic is very much like what Ben was talking about yesterday, except I swap in a policy under the hood. And so these top-level functions do the same thing of using the dummy argpack, which is always going to be empty, to select the policy, and then they call the policy function, right? And then the atomic type is just reflecting, like, it's a regular value, but we just access it atomically using these policy operations. And just like in Ben's talk, the critical section here turns off interrupts, and it also does the memory fences, right? It does the ASM volatile thing. So now, I can also do things like injecting type overrides, so that when I ask for an atomic bool, what I'm actually going to get is something that looks, walks and quacks like an atomic bool, but under the hood, it's a uint32T because that's the only thing the platform can do with exchange, right? It's aligned properly. I get the atomic instruction when I need it, and when I have something else that the platform doesn't support, then I get the policy operation, which is just turning off the interrupt and turning back on, for example. Nobody has to remember to align these variables correctly. Things just work. Well, now I have atomic. What would be really useful? We've already talked somewhat about it. Atomic bit set. I don't know why we don't have this in the standard yet, really. And it's just bit set plus atomic. Now, in the standard, of course, you can wrap atomic around anything. So you could wrap it around std bit set. But this came from a code review, where someone was trying to, I forget how they were trying to do it. They were trying to use a bit set, and they had some tasks which they had to wait for, and they were represented in the bit set, and when they would come in and be completed, they would clear the bit, and then they would go on. Well, what they really wanted was atomic bit set. They wanted one thing that does it, right? So why would I choose to say atomic bit set and not atomic of bit set? Well, a few reasons. For one thing, it's a bit simpler. But a big reason is some operations have to be removed, right? In particular, bit set allows you to do binary OR, binary AND, binary XOR, things like that. Well, if you have two atomic things and you do a binary operation on them, now you need some higher level way of assuming that's an atomic operation, right? And you don't want to bake that into the idea there. But basically, an atomic bit set looks just like a bit set, and you can do several things with it just like a bit set. Most of the common things you want to do are supported by the underlying atomic interface, so that's fine. Yeah, but it does have some limitations. Some limitations, like I said, are because the semantics would require you to think about this at a higher level anyway, like the binary operations. Shift operations are not yet part of std atomic, and most platforms have no instructions for that yet. The other limitation here is that because it's atomic, the underlying thing, like in a bit set, you can have an array under the hood, right? A bit set can be as big as you like, because you don't have to worry about keeping those bits coherent. It's not atomic, right? But when it's atomic, how are you going to keep coherency between all of the bits in the array? So at the moment, it's, again, that would involve making a decision which I think belongs at a higher level, right? You can always have a regular bit set that you use under a log, under calling critical section. So atomic bit set is a bit more specialized. All right, now, I don't have time to cover logging. That's a whole talk in itself. On Thursday morning, I'm doing an open content session on how our logging library has evolved. But here is a sample. This log line you see, everything here happens at compile time. The result of this is a log that says, hello CppCon 42 is an int. All of the formatting happens at compile time. You will notice that 42 is a value and int is a type, but I'm still passing them both as if they were going to this info function, of course, which is a macro. So there's a bunch of things that happen in logging that I'll talk about on Thursday morning. But this is what the call site looks like. You will also perhaps figure out that 42 is, while it is a perfectly good compile time value, as soon as we would pass that to a function, it would become not const expr. We don't have const expr function parameters, right? And yet, like I said, this entirely happens at compile time. There's no reason there should be any runtime cost here. Now, if there were runtime variables, then they would be formatted at runtime. But in this particular case, there's no reason it should be any runtime cost. I don't want people to have to remember to wrap 42 in an integral constant or things like that. You know, even if we have the more modern ways of doing that where they don't have to spell integral constant, they just put, is it CW? Constant wrapper, something like that. But no, they don't have to do that. They don't have to remember to do that. I've seen cases where perfectly reasonably humans forgot to wrap things up and it ended up in a runtime value where it should have been a compile time value. So I have fixed that. So in the end, you know, if the question, what is C++ good for? Well, if you Google this question, you find out that C++, most of the internet thinks that C++ is good for applications that demand high performance, efficiency, such as these, well represented at this conference. The top answers are always performance, performance, performance. This isn't a really good answer to me because C++, let's face it, doesn't have a monopoly on good performance. And in fact, it's not really good at raw performance because if you need super high performance, you always have to care about hardware. Yes? You always have to know the level below your programming, and that is most times the hardware. You always have to pay attention to details outside the language. Conversely, more or less any compiled language can get within about 20% of Fortran if you write it like it were Fortran. That's not my quote, by the way. Alex Stepanov said that. So what is C++ really best at? It's a combination of things, right? It's all of these things. We have layout control and low-level access that we can actually reason about. We have metaprogram, which allows us to write composable systems at compile time so that we get the maximum runtime efficiency that we can. And we get to build up abstractions. They might be small abstractions, they might be large abstractions. Either way, we can build up the abstractions and the affordances and make them composable so that you can express something at a very high level and it compiles down to nearly nothing, right? The combination of these things to me is what makes C++ a winner. Now, in closing, I would like to exhort you to think like a library developer. Even if we're writing, we all write functions, I assume. That makes us all, in some sense, library developers. A good thing I do is just step away from the problem, find a fresh perspective, try to think outside of the domain, try to avoid jumping to an implementation idea, right? And we've always done it that way isn't typically a very good argument. When I sit down to write code, I try to think abstractly as much as I can. In Bjarne's keynote, he said, don't do abstraction for abstraction's sake. I would say abstraction for abstraction's sake at the design phase is essential. That doesn't mean I have to implement things abstractly, but I like to think about things abstractly so that I can uncover new insights, right? And it might influence my implementation. It might not. I can decide separately how to implement something from how I understand its design. And we just have to try really hard to free ourselves of thinking in terms of implementation. But we just have to keep trying. So you can find most of the code snippets here were from these three libraries. The compile time, initialization, and build library, it's been mentioned before in several talks. There's a library called Stud Extensions, which is kind of like the way to make your utils folder publicly acceptable, I suppose. You make it a library and call it non-stud or stud extensions or something like that. And the bare metal concurrency contains the atomic and critical section stuff you saw. So thank you very much. And I don't think I have many time for questions because we took them during it, but I'll take your questions in the hall. But thank you.